The agenda is to discuss on public key cryptography, mathematics of public key cryptography, and RSA. Learning objectives of this session are: after attending this session, you shall be able to explain the public key cryptography, its advantages and disadvantages. You shall be able to understand mathematics of public key cryptography, that includes prime numbers, co-prime numbers, composite numbers, Euler's 5 function and Euler theorem. And you shall be able to describe RSA algorithm and RSA operations. First, we shall discuss on public key cryptography. So, public key cryptography, also referred to as asymmetric cryptography, is the another type that we are considering today. Earlier we had a look at symmetric encryption algorithm, and we focus more on block ciphers, and under this symmetric and block cipher type of encryption algorithm, how substitution and transposition can be used so as to convert original message into encryption message, which we call it as ciphertext. And also we have seen how ciphertext can be recovered back, addressing ciphertext and recovering original message or plain text. Those aspects we have discussed. Today we are focusing on asymmetric or public key cryptography. Public key cryptography is proposed by Diffie and Hellman in 1976. It basically uses two keys. One is a public key, second is private key. This pair of public key and private key pair for session key agreement between sender and receiver. Whenever sender wants to send any message towards the receiver, then there will be an agreement which is referred to as key agreement. In this particular session key agreement, sender is encrypting the original message by making use of public key and sends the message. The receiver, who should be having the private key, is getting this ciphertext from the sender and he decrypt it so as to get original message. Here the encryption and decryption are different. We are not going to make use of the substitution and transposition what we used to do in symmetric key. Here in public key cryptography, we are heavily depending on prime numbers. We shall go in depth into it. Let us look at how the sessions are being carried out in public key cryptography using encryption decryption. Now let us say Alice is interested in sending the message to Bob. Alice is having the plain text which is being referred as P, and on this particular plain text, by using the key, the public key K, he carries out some encryption function. Because of this encryption, the ciphertext comes out of it. This particular ciphertext will be sent on an insecure channel. Insecure in the sense, we expect that there can be possible threats and hacking on the ciphertext that we are sending. We assume like that and we send the ciphertext. This ciphertext and the public key distributed across the channel will be getting transmitted. Anybody can hold the public key. However, the power of public key cryptography is existing in decryption using the private key, which the receiver is knowing. From the insecure channel, the decryption takes place. The sender is receiving this ciphertext. Then by making use of private key, by making use of key generation procedure, he is producing the plain text. So the plain text which has been recovered after decryption is the application of the function of private key on the ciphertext at the receiver end. However, we should know that the power of private key and the public key generations exist in prime numbers, unlike what we have used in symmetric key, which is heavily dependent on substitution and transposition. So public key systems algorithms are based on mathematical function but not symmetric approaches involving substitutions and permutations. Public key algorithms involves the use of two separate keys, public key and private key. Moreover, it is usually impossible to deduce the private key from the public key, because the prime numbers and their features, which are providing the mathematical foundation in generating private key and public key, ensure that any such the private key based deduction should be very complex activity, so that the information which is getting transmitted over the insecure channel shall be safe and scrupulous, or hackers should not have access to that. The public key systems, an important element to the public key system is that the public key and private keys are related in such a way that only the public key can be used to encrypt messages and only the corresponding private key can be used to decrypt them. The advantages and disadvantages of public key systems are: the public key systems have increased security and convenience. There is no need to expose the secret key to insecure transmission medium. Digital signature, which prevents a sender from denying the validity of the message, play a very crucial role, and previously authorized message is the uniqueness of public key systems. The disadvantages of public key systems are that the public key systems are slower when compared to secret key systems. The mathematical operations involved in encryption and decryption are a bit complicated, and because of that we can see the activities in public key systems will be slower compared to that of secret key systems. They take much time whenever the message sent is too big. Now we shall see the mathematics of public key cryptography. Public key cryptography is using the mathematics of prime numbers. Primes are important because the security of many encryption algorithms are based on the fact that it is very fast to multiply two large prime numbers and get the result. Means encryption will be pretty fast. It is extremely computer intensive to do the reverse. However, decryption is requiring a lot of the computer resources and it is not so easy to recover back. Because of this only, there will be an increased security in public key cryptography. Mathematics of asymmetric key cryptography using the prime numbers we are discussing now. When you have the product of two primes, finding these two prime numbers is very hard. This problem is called prime factorization, and finding an algorithm which does it fast is one of the unsolved problems of computer science. So think that you are receiving a product of two primes. The product value you are getting. But what are the two prime numbers who are resulting in this product? This is very complicated problem, and in fact it is unsolved problems of the computer science. What is a prime number? A prime number is divisible by 1 and the number itself. Is 1 prime number? Yes, it is divisible by 1 and the number itself. Second one is, let us assume 2. It is divisible by what numbers? 1 and 2. What about 3? It is divisible by 1 and 3. What about 4? It is divisible by 1, 2 and 4. The definition of prime is indicating that it should be divisible only by 1 and the number itself. But in case of 4, we found that other than 1 and 4, we have got 2 also. Because of that, 4 is not a prime number. Like that, we can continue and check which are prime numbers and which are not. 3 groups of primary integers we can see. When we take a set of the integers, and this set we can actually regroup into 3 positive integers. First one is exactly one divisor, that is number 1. Second one is set of primes, exactly 2 divisors. Then third one is composites, more than 2 divisors. Like that, positive integers can be classified as number 1 and prime numbers and composites. A prime is divisible by 1 and number itself. 2 is a prime number, as is 3, 5, 7, 11, 13, 17 and so on. If you start with 1, then if you go on checking it up, all the numbers from 1, then 2, 3, 4, 5, 6 like that, which one of them is prime number, then 3, 5, 7, 11, 13, 17 and so on we get as prime numbers. They cannot be written as a product of other numbers. For example, 3. What are the products of other numbers? Other numbers in the sense other than 1 and 3. Do you have any other things? Similarly, 5. Other than 1 and 5, do you have any other products that result in the 5 value? So, check these positive numbers, then you do not get any. They cannot be written as a product of other positive numbers. There are an infinite number of prime numbers. Additionally, all numbers have exactly 1 prime factorization. When you split that number, what are the factors? If you check it up, then you will be seeing that 1 and 3, you will not be having 1. For example, in case of 3, what are the factors? Then you have got 1 only. In case of 5, what are the factors which result in 5? If you check it, you find that only one prime factorization will be there. Now we shall see what is the meaning of prime numbers, co-prime numbers and composite numbers. Please understand that these are very crucial to build our course on public key cryptography. The mathematics of prime numbers is very crucial for us. For that purpose only we are discussing. And when we go for public key cryptography related algorithms, then you will realize the value of the concept of prime numbers, co-prime numbers and composite numbers. Now prime number. This number has two factors. So if you consider 17, then 1 and 17. 17 into 1 is 17. And check with 2. So 1 and 2 only are coming here. So by definition, what are the prime numbers? We checked it. Any number which is divided by 1 and the number itself is a prime number. What about co-prime numbers? Now we pick up two values. Whether these are two co-prime numbers, are they co-prime numbers? We want to check it out. These numbers do not have common factors between given numbers. For example, we take 6 and 7. And what are the factors of 6 and 7? We have got 1, 2, 3 and 6. What about 7? We have only 1 and 7. And what is the highest common factor from A and 7? Then we will get 1. So, co-prime numbers, any two or above two numbers which are having a HCF which is 1 is referred to as co-prime numbers. Composite numbers. Number 18 has many factors. 2, 3, 6, 9, 18. Such numbers are called as composite numbers. So composite numbers are totally different. Okay, don't try to compare with prime numbers or something. It is totally different. So the composite numbers will be having many factors. So factorization only plays very crucial role in defining them. Consider 6 and 35. So as an example to check whether they are co-prime numbers. Now divisors of 6, if you look at it, 1, 2, 3 and 6. Divisors of 35, we have got 1, 5, 7 and 35. Now what is the highest common factor among 6 and 35? When you compare it, then we have only the value 1 is highest common factor. Thus 6 and 35 are co-prime numbers since HCF of 6 and 35 is equal to 1. Now relative primes are two numbers are relative prime numbers if they don't have any common factors other than 1. Since we know greatest common divisor concept, we can rephrase this as if A and B are relative prime numbers, if we have GCD of A comma B is equal to 1. Example, GCD of 25 and 39 is equal to 1. So 25 and 39 are relative prime numbers. Primality test. A primality test is a test to determine whether or not the given number is prime, as opposed to actually decomposing the number into its constituent prime numbers. We pick up any integer n which is greater than 1, and we are interested in determining whether n is prime or not. We know that the smallest primes are 2, 3, 5, 7, 13, 17, 19, 23. However, how can you carry out primality test to decide a larger number, whether the larger number is prime number or not? Number one is, so let us consider that 38,476. First we have to check whether the given number is odd or even. Now 38,476 is a even number. Even numbers are not prime numbers. Now let us take the second one, 4359. Now you sum up each of those digits, 4 plus 3 plus 5 plus 9. The sum of these digits is 21. So to be prime number, any integer value should be divisible by 1 and the value itself. But in case of 21, other than 1 and 21, we have got 3, we have got 7 and so on. Because of that, we can easily see that once we add it up 4, 3, 5, 9, and after that, if we find that the summation, whatever number we get, if it is not a prime number, then we decide that 4, 3, 5, 9 is also not a prime number. The given number is not a prime number. Like that we decide. Third type of test. Given a number n, how can we determine if n is a prime? Here what we do is, the answer is that we need to see if the number is divisible by all primes less than square root of n. For example, 9 you take it. What is the square root of 9? 3. So if the number is divisible by all primes less than square root of n, now we have to check it up. We have to check division by 1, division by 2 and division by 3. So between the 1, 2, 3, what are the prime numbers? All are prime numbers. And when we divide it with 9, then we are finding that it is divisible by all primes of square root n, which or square root of 9 is 3. So we divide it by 1, 2, 3. Then when you check it up, then what happened? Whether 9 is divided by 1? Yes. 2? No. 3? Yes. Now what happens is, two values can divide it, but the 2, which is the prime number, is not dividing 9. Hence it is not a prime number. So let us consider 97. What is square root of 97? After round off, we get 9. The primes less than 9 are 2, 3, 5 and 7. We need to see if 97 is divisible by any of the numbers. It is not. So 97 is a prime. Now you take the floor of 301, whether it is a prime or not. We found square root of 301 equal to 17. We need to check the number 301 by all the values starting from the 2 up to the value 17. 2, 3, 5, 7, 11, 13 and 17. Prime numbers. Up to 17, whatever prime numbers are for coming, that we have to take. And then after checking it, numbers 2, 3 and 5 do not divide 301. But the 7 is dividing it. Therefore, 301 is not a prime. Now, Euler's phi function, that we shall check it up. Euler's phi function is sometimes called the Euler's totient function, plays a very important role in cryptography. Phi 1 is equal to 0. There are total 4 rules of Euler's totient function. When you apply this function, the function of 1, that is Euler's phi function of 1 is equal to 0. Then phi p equal to p minus 1 if p is prime. This is the second rule to find the value of Euler's phi function n. Then third one is phi of multiplication of m and n is equal to phi of m into phi of n if m and n are relatively prime. Phi of p raised to e equal to p raised to e minus p raised to e minus 1 if p is a prime. So these are the 4 rules that are fulfilled by Euler's phi functions. Euler's theorem, the first version, a raised to the Euler's phi function n. So if it is resulting in mod operation of 1 mod n, then we have got first version of Euler's theorem. If a and b are co-prime numbers, then the second version, a raised to k into phi n plus 1 shall be equal to a mod of n. So in case of Euler's theorem, we pick up 2 values, one is a and second one is n. And if a and n are co-prime, then we find that the first version of Euler theorem and second version of Euler theorem are applicable. Euler's theorem examples. Find the result of 6 raised to 24 mod 35. By applying Euler's theorem, 6 raised to 24 mod 35, when you check it up, it is 35 equal to 6 of Euler's phi function of 35 mod 35, which is giving rise to value of 1. Find the result of 20 raised to 62 mod 77. If we get k equal to 1, on the second version, we have 20 raised to 62 mod 77, which is equal to 20 mod 77 into 20 Euler's phi function 77 plus 1 mod 77, and on that one mod 77 we apply. When we do it, we got 20 into 20 mod 77, which is equal to 15 value. Now with this background, we shall move into RSA. RSA is a scheme that uses public key for encryption messages. a corresponding private key for decryption. RSA stands for Ravesh, Shamir and Edelman. Those are the three people who have given the entire RSA algorithm. RSA study involves RSA operations and time complexities, investigation of attacks on RSA, applications of RSA and public key cryptography standard PKCS. In any cryptography, three important aspects we deal. One is a key, second one is encryption, third one is decryption. When you make use of these three operations, we are getting ciphertext and plain text. So, plain text and ciphertext with operation of key, encryption and decryption, they play very crucial role. In RSA also, the operations are key generation, encryption and decryption. So, key generation, that we shall consider now. Under RSA operations, key generation we shall consider. Under this, encryption key or public key generation and decryption key or private key generation. So, in case of public key cryptography or asymmetrical cryptography, we know that there will be two keys referred to as public key, and which is actually being calculated and transmitted at the time of encryption, and second thing is the private key, which is known to the receiver. He uses that and recovers plain text from the ciphertext. The RSA algorithm for key generation, we have to select two large prime numbers P and Q such that P is not equal to Q. Then we have to multiply them, N equal to P star Q. Then after that, we have to apply Euler's phi function on N value, that is P star Q, which is equal to P minus 1 multiplied by Q minus 1, where phi is Euler's totient function. Then we have to select an integer E such that this integer will be falling between 1 and Euler's totient function phi n, and GCD of this integer E value and Euler's totient function shall be 1. Means E and Euler's totient function n shall be co-primes. Then we calculate D equal to e raised to minus 1 mod of Euler's totient function n. Whatever the Euler's totient function value we have obtained, so e minus 1 we have to apply for that. What is e minus 1? If we are considering 3 as a value, then 1 divided by 3. And what is the mod of that phi n value? That we have to check it. Now public key, once we do this, then public key is involving E value and N value. Private key is D. So we had seen that how we can calculate public key and private key. Then when the message is coming following this key generation of public key and private key, we need to convert the given plain text using encryption to arrive at cipher. So that we are doing C equal to m raised to e, then mod of n on that. M raised to e, we do it, then we perform mod of n. And decryption, which is taking place at the receiver left side, is involving m equal to c raised to d mod n function. So like this, we perform encryption and decryptions. Now we shall take an example to check how this works. RSA operations, encryption key or public key generation. First we have to choose two larger numbers p and q. The product n equal to p into q is referred to as the modulus, and then we have to calculate the Euler's Totem function phi n. In order to do it, 4 rules to find the value of phi n, we have to check it. If the value of n, which is the modulus which we obtained by p star q or p multiplication q, if that n value is 1, then Euler's pi function, when we apply on 1, should give rise to 0. And if we are applying phi function on p equal to p minus 1, if p is a prime number, then we go for multiplication m and n, pi of m into pi of n, if m and n are relatively prime numbers. Then last one is phi p raised to e equal to p raised to e minus p raised to e minus 1 if p is prime. So these are the rules of arriving at Euler's Totem function. Now, once we choose the p and q value, once they arrive at the product n, then we are interested in choosing an encryption key e such that the GCD of e comma Euler's Totem function phi on the value of n shall be equal to 1. Note the pairs of integers e comma n is referred to as public key. In the step 3, we compute the decryption key d equal to e raised to minus 1 mod of phi n. D is also referred to as the private key. Recall that the Euler's phi n is the number of integers between 1 and n minus 1 that are relatively prime to n. Since n equal to p into q, the only integers in this range not relatively prime to n are p comma 2p, like that, up to q minus 1 into p. So the p value we go on multiplying with another value between the star 1, the 2, like that, up to q minus 1. And q comma 2q, like that, up to p minus 1 q. The q value we go on multiplying with 1, then 2, then 3, up to p minus 1. Hence, the Euler's Totem function phi n equal to pq minus 1 minus p minus 1 minus within bracket q minus 1 bracket complete equal to p minus 1 is multiplied by q minus 1. The number of bits b used to represent n is referred to as the key size B. So B log 2n, that we are considering as the size of B. Means size of B depends on n value, and log 2 we are going to apply it. Now we shall see how this is taking place. Let M be the message or plain text, and we use the modulus of M to denote the length of n. In the naive implementation of RSA, a message is split into multiple blocks, each of size B, except possibly for the last block. If last block is running short of the values, then we have to fill it up, the initial values by 0, followed by whatever values are available in that block. Then for each block Mi, we have to calculate corresponding ciphertext Ci as Ci equal to n Fi of mod n. This is what we have to use it. Decryption side, given a block of ciphertext Cp, the corresponding plain text is calculated as Mi equal to Ci raised to d mod n. A block plain text MP is encrypted as Ci using the equation 6.1. Will the decryption of Ci using 6.2 always return the original plain text? Put two different plain text correspond to the same ciphertext? All these questions we shall address. Now we shall take an example to understand this. Let us suppose that the RSA prime numbers we pick up are P equal to 3 and Q equal to 11. If we want to provide higher level of security, then P and Q value should be larger. Just for illustration purpose, we are taking P equal to 3 and Q equal to 11. Now N equal to P into Q means 3 into 11, which is equal to 33. And Euler's phi function N, we know that P minus 1 multiplied by Q minus 1. Now which is equal to P minus 1 is 3 minus 1, which gives to 2, and Q minus 1, which gives to 10. So we multiply them, and Euler's phi n function we get as 20. Now we have got n value, we have got phi n value. Choose a public key E equal to 3. Now the GCD 3, 20 equal to 1, because when we try to get the public key, then we have to ensure that the GCD of that value, then whatever value we get for Euler's function phi n, Euler's protium function phi n, should always give to 1. Then 3 minus 1 mod 20. So means 1 divided by 3 mod of 20. When you check it, it exists and is 7. So the private key equal to, D equal to 70. The key size is 6. Minimum number of bits used to represent n value. So the n value is 33. And when we convert into digital representation, what is the minimum block size? When we check it up, then we can find that the 6 minimum numbers of bits are used to represent n. Now we convert into block size of B. So then the given message 00111011, we note that it spans 2 blocks. The first block is 001110 or 14 in the decimal. The remaining 2 bits of the message are padded with zeros. Means we get only 0011, and so we have to fill the remaining by the 0 value, because we are interested in getting the key size, which is size the size 6. So we fill up remaining, then we get a 000011. After doing this, then we arrive at ciphertext for block 1, which is 14 raised to 3 of mod 33. We calculate, then finally we get the value 5. Note that the reduction modulo 33 may be performed at one or more intermediate steps. This helps maintain a bound on the size of numbers involved. And description we carry out. To carry out that, decryption is performed as 5 raised to 7 mod 33. Whatever value 5 we obtained here, then mod of 33. So after evaluating that, we finally end up that the value will be 14. The ciphertext for block 2 is 27, and decryption of this ciphertext yields 3. With this, we come to the end of the session, and we are going for the other in-depth activities in the next session. Thank you.